Photoelectric effect refers to a phenomenon in which electrons, called photoelectrons, are ejected from a material such as a metal as a consequence of the absorption of energy from light. So this is a metal plate. Now, if the frequency of the light isn't high enough, no electrons will be ejected. But if it's of the appropriate frequency, then electrons are ejected from the metal. So to summarize this observation, below a certain threshold frequency, no electrons are emitted from the material, and this is regardless of the intensity. So if you don't have the appropriate frequency, even if you go to more intense beam, electrons won't be ejected. It requires a certain threshold frequency in order for the electrons to be removed from the metal. However, once you're at the threshold frequency, increasing the intensity will result in a greater number of electrons being ejected from the material, in this case a metal plate. So here's our metal plate, we go to higher frequency and boom, more electrons. I'm sorry, a higher intensity, and therefore more electrons are ejected. If you go above the threshold frequency, then the kinetic energy of the electrons is increased. So and that's represented with this, and then higher frequency, and the larger line represents electron with greater kinetic energy. This phenomenon is actually better described using a particle model for light. The energy of the light particles, which are called photons, is represented as E equal to Planck's constant times the frequency of the light. So this was the equation formulated by Planck to describe the behavior of light emitted from black bodies. Einstein then used this quantization of light energy to describe and help to understand the photoelectric effect. In fact, Einstein won the Nobel Prize for Physics for this particular contribution. So to describe the light as photons instead, then if you have photons that are of not the appropriate frequency, regardless of the intensity, i.e. number of photons, so more photons impinging on the metal plate does not result in any electrons being ejected. So each individual photon you can think of as not having enough energy to knock out an electron. However, if you go to photons with higher energy, now these can eject the electron. And this is a consequence of the fact that the energy of the light is related to the frequency of the light and not the intensity of the light beam. Of course, if you go to higher intensity at the appropriate frequency, then you'll get more electrons ejected from the metal plate. And we're representing the greater intensity with a greater number of photons. I'm showing in my simple diagram. And then, of course, if you go above the threshold frequency, so this is the frequency. The blue light will represent that as one frequency. We go to a higher frequency represented by the purple light, and now, boom, electrons with greater kinetic energy are ejected. And this kinetic energy is equal to the frequency, the energy of the light, Planck's constant times the frequency, minus the work function for the metal, which is basically the energy required to move an electron from the material. So to work an example problem using this equation, this problem starts, the work function for cesium metal is 3.42 times 10 to the minus 19th joule. So that's the energy required to eject an electron. Part A, calculate the minimum frequency of light required to eject an electron from the metal. And B, calculate the kinetic energy of an electron ejected by a photon with a frequency of 1.0 times 10 to the 15th hertz. So first we're going to find the minimum frequency of light required to release an electron from the metal, and then we're going to use a frequency that's a little bit higher than that, a little more energetic, and calculate how much kinetic energy an ejected electron would have if we use that one. So we're going to need this relationship. Kinetic energy of the electron is equal to h nu minus the work function. In the case of calculating minimum frequency, we're going to set h nu, the energy of the photon, equal to the work function, dividing both sides by Planck's constant, and then inserting in 3.42 times 10 to the minus 19th joule for the work function that was provided in the problem, and then 6.626 times 10 to the minus 34 joule seconds is Planck's constant, and this results in a frequency, minimum frequency of 5.16 times 10 to the 14th hertz. In part B, we're going to calculate the kinetic energy if we use a frequency that's a little bit higher. So Planck's constant times the frequency 1.0 times 10 to the 15th minus our work function 3.42 times 10 to the minus 19th joules. And this is a pretty straightforward calculation. 3.21 times 10 to the minus 19th joules would be the kinetic energy of the ejected electron.